Welcome back, students. So, today we will cover the fourth part of our lecture series on solar energy. And in the previous parts, we have covered mostly on the introduction of solar energy, and then we have also seen what are the working mechanism of solar cell based on PN junction. In our last part, which is the third part, we have covered what are the factors that affects the efficiency of solar cells and how we can improve the efficiency by implementing certain strategies such as using concentrated solar power or multi-junction solar cells or putting anti-reflection coatings, how we can improve onto the efficiency of the solar cell. Today we will look into more the commercial part of the solar cell which have been available and what are the basic structures of these commercial solar cells. So basically, the solar cell have been always divided into three generations. These are the three generations solar cells. This was the first solar cell that was been implemented commercially, which was based on wafer technology, in which silicon was used as a basic material. So the first solar cell that was available commercially was monocrystalline silicon solar cell, which was able to give the efficiency about 25 now. Okay, then we have polycrystalline silicon solar cell. Since the manufacturing of monocrystalline solar cell is quite difficult, and because of that the cost is very high for the monocrystalline, while polycrystalline the cost is less than the monocrystalline. Okay, but the performance wise it is not as good as the monocrystalline silicon solar cell. So that's the reason, what we have the efficiency of about maximum efficiency is about 20%. Okay, and then there was also few development of multi-junction solar cells, where initially people have started using material of different band gaps, and then it was able to produce a good efficiency about 40%. Now it has been increased up to 47%. I will come to that. Then the thing is that since the wafer based solar cell requires lot of material, I mean to say the thickness of wafer is about uh, 300 micrometer, okay, which is like 0.3 mm. Even that much amount of material, if you use it, it's quite costly in the end. Okay, so to reduce the cost, there is a second generation solar cell which was launched, which was based on thin films. So people have started using amorphous silicon thin films. Okay, so in this case the cost was much lower, but the efficiency at the same time was also lower because amorphous silicon has a lot of recombination centers, and because of that there is a recombination problem increases in amorphous silicon. Similarly, as I've told you in my previous slides, that there are other very good band gaps like cadmium telluride, gallium arsenide, copper indium gallium arsenide, selenide. This has the optimum band gap of around 1.4, and so this was developed in form of thin film, and which was able to bring the efficiency about 17% to 20%. And then later in the third generation, there are new technologies that have been coming up with a very low cost but with very high efficiency. So there are like dye sensitized solar cell. Then this dye was replaced with quantum dots. Okay, so this is called as a quantum dot sensitized solar cell. So it's one and the same thing. Here they use dye, and here people use quantum dots. We'll come to that. Uh, then we have organic photovoltaics. So it is based on polymer. So since polymer material is very cheap, so this can give us a very cheap alternative to produce electricity from the solar energy. Similarly, there are other solar cells which is based on polymers. Then there are new materials that are coming up which are called as perovskites, and you have been hearing this in our department, about perovskite solar cells. So people have been working now into this field because it can produce high efficiency, and the cost of this material is also not too high because it is made up of normal metal oxides. Okay, so we'll come to this one by one. Let's look at how these have been differentiated in terms of cost and efficiency on this in this plot. So you can see here, the first generation solar cell was mainly very costly. The efficiency is good enough to be utilized, but the cost factor is still very high, and still, people are reluctant to use the solar panels, because which is based on this first generation solar silicon solar cell, and the cost is still very high. And this is mainly due to the reason of manufacturing silicon, because I don't know if you remember, there are certain techniques to prepare silicon single crystal silicon solar cells. Though silicon is the most abundant material, if you see silicon, it is available in sand. So there is abundant amount of sand on this earth surface, and so we can extract silicon out of that. But still, the problem is the manufacturing of single crystal silicon is quite a tedious job and requires very sophisticated equipments, and because of that the cost is very high. But second generation solar cells, yes, the cost reduces because we use very less amount of material because it's in form of thin film, so the material required is less. But again, the efficiency, we have to compromise with it, because the efficiency is below 20%, and so the cost is low, efficiency is also low. It's quite simple. But the third generation, there is a lot of research that has been going on, that not only we can produce high efficiencies but also with lower cost. Okay, so the people have been working into it, but still it is under development, and commercially it is not yet been available. Commercially, yes, people have been using it, but in more sophisticated applications. For example, in satellites and other places, where you require solar cells of high efficiency. So there, the people don't care about the cost. So the multi-junction solar cells comes into this category. So we'll come to that one by one. So let's consider first the most simplest thing is the silicon solar cell. We have seen how it works. By creating PN junction, we can able to develop the electric field into my solar cell, and which is able to separate my electron and hole pair and can produce my electric current. Okay, so this is the basic structure. We have already seen what are the basic components of this solar cell. It contains p-type silicon. Okay, this is the p-type, which is the major absorber material. So most of the light irradiation is been absorbed in this layer, which is 300 micrometer thick, while there is an n-type semiconductor or silicon which is laid over it. So this region is the PN junction. As one of you has asked me that, do we have to irradiate only on the junction? It is not true. See, the important thing is, as I've told you in the basic mechanism of solar cell, is that any semiconductor, when you irradiate with light, if the energy of my photon is higher than the band gap, it will produce electron hole pair. Okay. The only important thing is that we have to separate this electron and hole pair. Okay, and that is done through by applying electric field, or by producing its internal electric field. Okay, so the role of PN junction is to only develop that electric field, the required electric field. Okay, so this is the main semiconductor material which is absorbing light, and which is creating electron hole pair. But because of the junction, there's an electric field that has been created in this whole structure, and because of this electric field, the electrons will start moving towards my n side, while the holes will start moving towards my p side. Okay, and there is no recombination that is been taking place. Otherwise, it's very difficult for the transportation of the electron and hole pair, because the diffusion length of both these charge carriers are very small. 300 micrometer is a huge length for the electron and hole pair to travel without an electric field. Okay, So there must be an electric field that should be produced, and that is produced through my PN junction. So you, for that PN junction, you don't need to put a very thick N type or very thick P type. Only a thin layer is enough, which can produce enough electric field for separation of electron and hole pair. So you can see there is an this N type is laid over P type. There is absorption of light on in N type also, but it's very small, because you can see the thickness is about 300 nanometer. Okay, so 300 nanometer, most of the uh, light will pass through it. And why you require this kind of very thick silicon cell is that because the coefficient absorption coefficient of my silicon is very small. Okay, what I am trying to say is that you require a very thick material for my all the photons to get absorbed in my silicon. That is a drawback of silicon, that though it has a very good band gap and it is very abundant as well, but at the same time the absorption coefficient is very less. That means the light which is being absorbed by the silicon is very less. It requires a very thick material for the all my radiations to be absorbed, and that's the reason you used a thick silicon solar cell, and which is a drawback, because you are using a large amount of material for developing this solar cell, because 300 micrometer, it's quite high. I don't know if you know the cost of a silicon wafer. A silicon wafer of about 4 inch in diameter, it will cost around $100. Okay, you understand, 4 inch diameter. It's quite small, and single crystal solar cell, which will cost about let's say 7,000 rupees. Okay, $100 is about 7,000 rupees of your silicon wafer. So, this is, because of this thick layer, the cost of this silicon solar cell goes very high. Okay. Then there is another thing that you can see here, that is N plus region and P plus region. Okay. So N plus is nothing but heavily doped N type silicon. Heavily doped means that it contains large number of dopants. Okay, which will, so this is N type, so which will provide large number of electrons. Okay, so it is heavily doped, so there is large number of electrons in this region, while this is heavily doped P type. So heavily doped P type means there is large number of holes which have been there in this region, in this layer. Okay, why it is been done is that, since when we irradiate with light, electron and hole pairs are generated in this region, which is the absorber layer. Okay, electrons will start moving in N type, while the hole will start moving at the bottom, P type. So when electron reaches this N type, we want to be sure that it does not recombine with any of the holes present in this N type. Okay, while similarly, we have to be sure that the holes which are reaching in the p type, okay, should not recombine with any of the electrons in this p type. So to be very sure, okay, we just heavily doped with holes here, so that if there is any extra minority charge carrier, which is electron in this case, it will first recombine with the electron which have been present there. So whichever the photo generated electrons, when it comes here, there is no hole for recombination. So we are making an extra surety that there are no recombination that take place in this part or in this part. Okay, similarly here, there is a lot of electrons. So if there is any holes that have been present, this hole will be covered with the electrons which are already been present. So when there is a photo generated electrons, when reaches the N type, it will not recombine with any of the holes in that case. So this is the main motive to make heavily doped N side and heavily doped P type in this case. Then obviously there is a back contact which is made up of metal, so that the current will be flowing through this back contact, and we just connect with the outer load. While at the top side there is anti-reflection coating to remove all my reflection part, as well as there is a texture effect that has been given here. You can see this is texture effect, textured surface, so that it is made rough, so that no reflection that take place at the same time. Then there is this front contact metal through which all your electrons is been collected, and it flows to the outer circuit. So this is the basic component, and this is how the practically your silicon solar cell has been designed. This is the top layer. You can see this is clearly been uh, you can see these are lines which are actually nothing but a metal contacts. This is the main metal contact through which all your small part, the charge generated in this small part is collected in this main lines. While we have polycrystalline, you can see polycrystalline means there are there are large number of grains that have been there, so you can clearly see the grain structures in this. So this is not a single crystal. This is grain structure. You might have even seen this practically when Aurora sir has brought this during his lectures. You know, when he used to actually take an invited talk, he used to bring this kind of solar cell, and it was been circulated among the audience. So you might have seen this during this kind of lectures given by Aurora sir. So this is how basically your a single solar cell of silicon looks like. Okay. Now, as I've told you that the major drawback with my silicon solar cell is that we use large amount of silicon. Means the thickness of my absorber layer is about 300 micrometer. Okay, and because of that, the cost of your cell increases. So to avoid that, we have to decrease the amount of material that is being used. So that's the reason now thin film solar cells came into picture. So the materials is been produced in form of thin film, where you don't have to use 300 micrometer, but even 1 micrometer or 10 micrometer will do my job. So the amount of material that is being used is about almost 300 times less. So your cost will automatically also come down with that. Okay. So there are thin films of your gallium arsenide, cadmium telluride have been already available. Okay, then there's CIGS, which is having a band gap of 1.2 and produced in thin films can produce up to efficiency of 21.7. These are the maximum recorded efficiency till now. Okay, then we can also produce a silicon thin films, but which is amorphous, because as I've told you that crystalline silicon has a very low absorption coefficient. So if you produce a crystalline silicon thin films, it will not able to absorb, or it will able to absorb only very small number of photons because of the absorption coefficient. So it has to be seen that it is hydrogenated silicon, amorphous silicon, which can, depending upon the hydrogenation, depending upon the hydrogen doping into it, the band gap varies from 1.2 to 1.7. So you can also tune the band gap depending upon the hydrogenation. And at the same time, this amorphous silicon also have a good absorption coefficient because it has a random structures. And amorphous doesn't have any ordered structure. It has random structures, and because of random structures, there's a lot of internal reflection that take place, and because of that reflection, you have a better absorption coefficient. So that's the reason amorphous silicon can also be produced in form of thin film. So this will reduce my cost drastically. So this is the basic structure or construction of your cadmium telluride solar cell. Even the gallium arsenide is the same. Okay, so you have a back contact here, which is the metal contact made up of gold. Then there is a cadmium telluride absorber material, which is of about 100 micrometer, sorry, 10 micrometer. Okay, and then you have a 100 nanometer of your CDS, which is cadmium sulfide. Uh, okay, there is a mistake here. I have to write CDTE, so there was some mistake at this part. Okay, anyhow, that's what I was remembering. Why I've written calcium telluride. Okay, this is cadmium telluride. This is telluride. Okay, so you have a cadmium sulfide also layered 100 nanometer. So both this is an hec- heterojunction semiconductor. That means that it will form a PN junction. So this is basically N-type, while your cadmium telluride is a P-type semiconductor. This N-type semiconductor. Because of that, you form a junction, and that junction will provide you the required electric field for the electron hole pair separation. Okay, And so over this cadmium telluride you have a transparent conducting oxide which act as a conducting layer. Like in silicon solar cell we have a top contact. Here you have a transparent conducting oxide as your top contact. Transparent conducting oxide is nothing but it is kind of transparent like what we have it in glass, but it is also conducting like ITO is indium tin oxide, or FTO, which is fluorine tin oxide. Now these are the two materials which are very good as a transparent conducting oxide, where it is transparent, so it will allow all my light to pass through it. At the same time, it will also give me the effect of conductivity like metal. Okay, so it has a property of metal conduction as well as a property of an insulator which is transparent. Then at the top there is a glass which gives stability for my structure, and over that glass we put some anti-reflection coating, so there is no reflection that takes place. So the light pass through it, and you see that this is how the basic construction of your CDTE or also gallium arsenide solar cell. This is again the basic structure of your copper indium gallium arsenide CIGS. So you have a glass. Here they have reversed the thing. It's depend upon the design that is been required. So over the glass you have a coating of metal contact of molybdenum 350 nanometer. Then over that molybdenum, then you have your main absorber layer which is CIGS. Okay, and to form a PN junction you deposit again a 50 nanometer of cadmium sulfide. Then there is a ZNO layer which works as a transparent conducting oxide, and above it there is an 100 nanometer of magnesium fluoride, and magnesium fluoride is a very good anti-reflecting coating material. So whenever there is an anti-reflection coating material, mainly this magnesium fluoride is being used. So you can see. Uh, so this is the basic structure. You have PN junction in form of CIGS and CDS. You have two contacts. One is molybdenum and ZNO, front and top, front and bottom contact, and then you have anti-reflection coating. So this is these are the main common components that have been required to build a solar cell. This is again a amorphous silicon solar cell. So amorphous silicon solar cell actually has a PIN kind of structure. So there is an absorber layer, while there is an N-type silicon amorphous silicon here, and there is a P-type SiC. SiC is silicon carbide. Okay, so which is heavily doped P, and this is heavily doped N. The similarly that what we have in silicon solar cell. You remember that this is N type, P type, and we have an absorber layer in form of I. So here also is the same scenario here. So you have a main absorber layer is your amorphous silicon, hydrogenated amorphous silicon, where your H is this, and there is a contact here. Uh, and there is N type and there is a P type. So at the top there is also this indium tin oxide which give you the conducting part of it, and it's a transparent conducting oxide. Then there is a glass, then there is an anti-reflection coating over it. So this is how your again the amorphous silicon structures look like. It's similar to the silicon structure, but the amount of the thickness of this layer is very less. It's about 10 micrometer something, and even these layers are very less. So the amount requires is very less in this case. This is the multi-junction solar cell. As some of you have requested me that they did not understand the working of multi-junction solar cell in my last series of the lecture. This is how it looks like. As I've told you, the basic concept of using multi-junction solar cell is quite simple. That when we use a low band gap solar cells, okay, like for example germanium, which has a band gap of around zero point 0.8. In that case, the large number of photons will be absorbed for sure, but at the same so it will produce large number of photocurrent. So current that is been induced in that low band gap solar cell is quite high, but the problem is the voltage. As I have told you that there is a voltage factor, and voltage factor is nearly about if you consider approximate value, it is always zero point 0.4 volt less than the band gap of your material. So the maximum voltage it can produce, okay, will be zero point 0.4, will be the band gap minus zero point 0.4. So let's say for example germanium, the band gap is zero point 0.8, so minus zero point 0.4, so it will give me about zero point 0.4 of voltage. Okay, so even the germanium solar cell, if it gives me high photocurrent, at the same time the voltage developed in that solar cell is very low, and in the end when we want to consider the output power, we have to multiply these two things. So the voltage into current will give me actually less power because the voltage is very less. Similarly, on the other side, if I consider my large band gap semiconductor, let's say about 3 ev, or let's say even 2.5 ev. Okay, in that case my voltage developed will be high. Let's say 2 ev or 2.5 ev can give me the voltage of about 2.1 ev maximum voltage, but the number of photon that have been absorbed in that large band gap will be less, so the current produced it will be less. Okay, so the total power you will get is less. So what, so that is the reason there is always a compromise between a requirement of high voltage and high current. So that's the reason 1.4 is an ideal band gap of a semiconductor which will produce a good amount of voltage and good amount of current, though not the highest. Okay, it will produce enough voltage, enough current which will produce my large power. Okay, similarly in multi-junction solar cell we actually combine the feature of low energy band gap or low band gap semiconductor and high band gap semiconductor. Okay, so you just combine the feature of these two semiconductors together to produce my better voltages and better current. Okay, so let's say for example, this is the most advanced form of multi-junction solar cell which has recorded the efficiency of 47%. This is the highest efficiency ever been recorded. Okay, so in this case you have a solar cell. See, you can see there are actually four layers or four junctions that have been created. So you have gallium indium phosphide which has a band gap of 1.9, then you have aluminum gallium indium arsenide which is 1.6. Then there is a gallium indium arsenide of 1.4 ev, and then there is a gallium germanium silicon solar cell which is 0.67 ev. So all this is able to develop my, because the light will be absorbed at a different part of this semiconductor, one two three, there are three different semiconductors, and this will provide me a light will be absorbed in all this part, and the voltage that has been developed will be the addition of all these four layers. Okay, while the current that has been developed is only due to these layers. Okay, so when you multiply these two things, you will be able to produce a large number of power, and which will give me the efficiency about 47%. Similarly, in silicon solar cell, the scenario is the similar thing where you use three different multi junctions here. One is your amorphous silicon hydrogenated silicon. Then we have amorphous silicon germanium H, where silicon and germanium are added together and hydrogenated, which will give me a band gap of 1.54. Then we have again different amount of hydrogenation that is being created, and which will give me the again my band gap 1.37. So you use three different band gaps here, and you can see that it produces p type, I and n. P and n junctions are just to create my pn junctions, while your I is an absorber layer. Okay, you can see all these colors have been clearly mentioned here. Orange is p type, blue is n type, while your middle one is your absorber layer, and then it is obviously given the basic structure which is ITO, which is a top contact. Okay, and then there is a bottom contact in form of a silver here, and again there is anti-reflection coating, and then there is this texture effect that has been given. So all this multi-junction solar cell will provide me a very good amount of band gap. Okay, so I hope now the concept for multi-junction solar cell is quite clear now. So let's go to the new upcoming solar cell, which is based on dye sensitized solar cell. Here the dye sensitized solar cell is based on a dye which absorbs the solar light. Okay, so dye is the material which acts as an absorber for the solar light. In this case, what we have here is the basic structure is in form of TiO2, which is a titanium dioxide, and which is coated with dye. Okay, a certain colored dye, normal dye that we use, which has been these are organic molecules and which can absorb certain wavelengths of your light. Okay, so it absorbs this, and this dye also has like kind of HOMO and LUMO levels. HOMO level is the highest occupied molecular orbital, while LUMO is the lowest occupied molecular orbital. So these are HOMO LUMO levels. So one light is excited here, it makes a transitions, it makes an electron and hole pair. So electron goes to this LUMO levels, and then since this level is more negative than the conduction band edge of your TiO2 material, so this is actually a anode material, this is TiO2. Okay, so the electrons immediately transfers to this conduction band of your TiO2. Okay, and you can see here this electron transfers to the TCO. TCO is transparent conducting oxide. Okay, and then it flows to the outer circuit. It is brought back to my cathode, which is made up of normally platinum. You can see this is platinum, and then there is an electrolyte. So this electron is given to my electrolyte, which reduces, which is actually based on I3, and this is reduced here, and this I3 captures whole from my dye molecules, okay, or provides electron to this dye molecule. So the holes which is produced in this part recombines with the electrons of the electrolyte, and whole circuit is complete. So getting my point. So the again I would like to tell you that there is a light which falls onto my dye molecules which produce electron and hole pair. Okay, the electrons which are developed in my LUMO levels have been transferred to the conduction band of my TiO2 material. Okay, and through this conduction band it is connected to my TCO, which provides my electrons to the outer circuit and is collected at the other end at platinum. Okay, here is the platinum, and this platinum gives these electrons to the electrolyte, which later on provides back to the HOMO level of my dye, and it recombines with the whole. So this is how the whole circuit is been complete. Okay, so this is actually the best part of this dye sensitized solar cell. It is very cheap. You dyes, it's very cheap. TiO2 material is like 50 rupees per kg you will get. So it's again a very cheap material that is being used. So this TCO glass, it is available. Yes, the platinum is costly, but except for platinum you can also use other metals as well. And this electrolyte is also very not so costly. So in the end, whole this setup provides a very cost effective alternative for the silicon based solar cells or the other multi junction solar cells. Okay, and it is very easy to prepare. This can be even prepared in your labs normally by you, or also by at your home. You have to just take TiO2 material, dip it in dye, put it over TCO, just coat it over it, and produce another metal contact. You can just fill it with some electrolyte, and you can produce this kind of silicon solar, this kind of dye sensitized solar cell. So the problem is the efficiency of this material, which is only 11%. Okay, and the major problem in this case is the lifetime. The lifetime is just very few days. It doesn't provide any alternative for the lifetime, because dye usually get degrade very fast on the TR2 material, and dye get removed from it. So in the end, if there is no absorber material, no light will be absorbed. So lifetime is very less. It can be even 1 day, so less. But the cost of this material is very less, so people are working into this. And rather than using dye, as I've told you, there is a quantum dots that are being used nowadays. So rather than using dyes, there is a certain material, quantum dots are the nanoparticles, okay, which is having a size with the range of 1 to 5 nanometer. And some materials, when we like CDS, cadmium sulfide, when we go at certain nanometer size, it has a quantum size effect, and which will able to produce a band gap of certain wave of certain energies. So rather than dye, there is another material called quantum dots have been used. Okay. So then there is an organic solar cell which is based on polymer. Okay, again the polymer has, it's an organic compound, and which can also have this HOMO and LUMO levels, which are actually called as donors and acceptors. So again, when the solar light falls onto this donor and acceptor level, it will produce electron and hole pair, and this electron and hole pair is conducted to the outer circuit, and it can produce electric current. The problem with this is that the efficiency is very low, up to 1 to 4%, but it is very cheap and very flexible. That is the most or the best part of this material is. It's so flexible that you can just roll it, put it in your pocket, and carry wherever you want, and you can use that as a mobile charger. You can see this. It's used as a mobile charger. It's very flexible. It's like plastic, right? It's a, you can see even this bag is coated with this solar cell, and light absorb, and it can produce the required power to charge your mobile phone or run your radio, or there are several things that can be run on this kind of polymer solar cell. Recently there was a lecture where the people from Pune has developed this kind of cap which is covered with polymer based solar cell, and this cap can produce electricity to run their fans at the top of it. So they have a cap which is made up of solar cell and the fan. The electric power to the fan is given by your polymer based solar cell. But there are also a few research which have been going on, and they can produce a tandem structures which can produce efficiency of about 17%. So it's due to its flexibility, you can put anywhere. You can just put it on your roof, you can put it on your windows, and you can, wherever the solar sun is available, you can just lay this kind of polymer solar cell, which is very cheap. It's like cost of plastic, and so it can be easily be laid down anywhere wherever you want. Then we have another type of solar cell which is coming up, which is perovskite solar cell, and perovskite has a certain crystal structures, and this crystal structures is able to produce a band gap of around 1.48 to 2.2 ev depending upon which material that have been used. And this crystal structures have been used as a replacement for the many other material, and which can produce a good amount of efficiency as well. So people have been, this is very fast growing technology, where at the start it was able to produce only 1%, but nowadays it is able to produce even 22% of efficiency. So this is very fast growing technology, the perovskite solar cells. And you can see this is the a chart where you can just pause the video, and you can look at very closely, and you can see this is the cell efficiency, and this is the years how it was developed. You can see the maximum efficiency that has been obtained is with multi-junction solar cell, which is up to 47.1%. This has been developed in NREL in US, which is National Research Energy Laboratory. um, so you can see there are, these are all, mostly the purple colors are all multi-junction solar cell which is producing very high efficiency. Then there are blue, which is crystalline solar cell. There is also some emerging solar cell, dye sensitized thin film solar cell. So you have to just pause this video and look very carefully how this has been uh, distributed. Okay, so that's it for today. We will cover in the next part the part in which I will cover mostly on the solar panel part, the technical part of the solar panel, and then we will also look into the solar thermal for this. So thank you. We can have the question and answer session on our group, or as well as you can ask me on our Google Classroom. And today we will be also having this lecture on Zoom where you can ask your question as well. So thank you.